Good morning. Thank you all for selecting this lecture on hurricanes, floods, and fires, oh my, predicting extreme weather and hazards from days to decades. My name is Ben Kurtman. Before we begin, I just want to remind you can submit any questions at any time during my presentation. Just use the Q&A box and feature located on the right side of your screen. After my presentation, I'll do the best I can to get to all of your questions as quickly as possible. All right, so hurricanes, floods, and fires, oh my. I want to talk about efforts here at the University of Miami, efforts that we lead internationally to improve our predictions of hazards from days to decades. So first chart I always like to show is to think about the amount of money that it costs U.S. government or people associated with weather and climate disasters. So this is a picture of just those weather and climate extreme events that cost over $1 billion. So each one of these events on this chart corresponds to a minimum of $1 billion loss. And you can see they include fires, drought, tornadic activity, hurricanes, hail, all of these events. If we had advance warning, if we could plan 2-3 weeks in advance or a season in advance, we might be able to mitigate many of these financial damages and loss of life. One example I like to bring up is from January 2018, and this was a big rainfall event that followed a long period of drought. So big drought, all the plants on the hillside died for a long period of time. Then we had this big rainfall event and big mudslides, and a number of people perished. This is actually not too far from where I grew up. In Santa Barbara, California, there was these big mudslides. A lot of people died. We actually were live with our prediction system that we developed here at the University of Miami, and I'm going to show you an example of how we were able to forecast that particular big rainfall event and others. More temporally local, just very recently, you all heard, I'm sure everybody has heard about the major event in Texas, all the power issues. I just want to bring up my pen here so I can highlight some features here. So in this panel on your left, these are forecasts of temperature. These are various models that are predicting temperature. This one right here that I'm circling right now, this is the one we actually run here at the University of Miami. This is the forecast we run here. And this is the average of all these various forecast models. And this is 2 to 3 weeks in advance of this big cold event that happened in Texas. So if Texas had decided to pay attention to this forecast, they could have potentially mitigated some of those damages and those extreme fuel costs that happened during this most recent cold spell. So can we predict hazards weeks, months, and even years in advance? I get that question all the time. It's a really important question. And the first thing I always tell people is, you're right. We can't predict the weather much beyond 10 days. So even today, I get phone calls from people, I'm getting married June 17th, 2021. Is it going to rain? Can I have my wedding outside? And I have to tell them, I can't tell you that. I can't tell you if it's going to rain June 17th, 2021. But I might be able to tell you something. And the something I can tell you is there a greater chance it's going to rain this June 17th than on all other June 17th? So is it an increased chance of heavy rainfall? And the way we can do that is there are components of the climate system: the ocean, the sea ice, the snow cover, the land surface temperatures, the soil moisture, plants. All of this stuff evolves very slowly and can shift the weather. And I'm going to show you a really nice example of that. And so when we talk about predicting weeks and months and even years in advance, we're talking about predicting those slowly evolving components. The ocean is one of the big examples. And we're talking about the shifts in the statistics of weather go along with that. So I might be able to say, well, this hurricane season is going to be more active than say 2 or 3 years ago. Or I might be able to say this coming winter is going to be really wet and snowy, for example. Now, all predictions must be risk forecasts or probability forecasts. Like I said, I can't say it's going to rain on June 17th, 2021, but I can say it's a much higher risk this year that it's going to rain during your wedding, or a much lower risk. And then you have to decide if you're going to plan your wedding to be indoors or outdoors. And so in order to produce these good, well-calibrated risk forecasts, we have to use multiple tools, because some tools are predicting good at this, and some tools are really good at hurricanes, some are good at rainfall in the Pacific Northwest, but not so good in the Southeast. And so we bring all of these tools together in order to make the best well-calibrated forecast of extreme weather and climate around the globe. So it's really this systems integration that we're bringing together. And that's where we lead things here at the University of Miami. We develop one of the tools, we use one of the tools, but our leadership role that the federal government has enlisted from us is to do the systems integration, to bring everything together. And I'll explain a little bit more about that in a few minutes. So just to think about prediction across timescales, these various timescales. So everybody, I'm sure, is familiar with weather forecasts. You know, the weather forecast for this afternoon is pretty good. It's going to be a pretty reliable forecast. And you can see the skill falls off fairly rapidly as you go out to, say, 20 days. There's this other time scale, this what I'm going to call subseasonal. It's sort of 30 to 60 days. And you can see the skill is a lot lower. And that's another reason why they have to be probabilistic. So you really have to think about, well, is there a 60% chance or 70% chance of something happening? So we have to think in those risk terms and probability terms. And there's phenomenon, slowly evolving phenomenon that gives us some reason to have skill. And I'm going to show you one of those phenomenon. And in fact, it's really strongly related to hurricane activity. And so that's one of the things we're really trying to tap into. So I'm going to talk a little bit about this subseasonal forecast timescale. And this is sort of the new turf. This is really an area in the world of weather and climate prediction that we're just now having rapid breakthroughs and making rapid progress. And so this is an area where we're trying to break through in our systems integration and getting it to become an official government forecast system. So here we're working at getting that done, and I'll talk about that in a minute also. On this little bit longer time scale, this seasonal forecast time scale, this we've been doing for years. And so 10 years ago or so, NOAA, the federal government, the National Oceanographic and Atmospheric Administration, came to us, came to the University of Miami and says, can you guys do this systems integration? Can you build this system for making seasonal forecasts? And we said yes. And of course, they gave us some resources to do that. And we built this system. And now this system, and I'm going to talk about it at length, the system is operational. It's an official government product. It's we have to deliver on time, in real time, all the time. There's no room for missing a forecast. It's not acceptable. We have to do it, and we do it, and we have been doing it since 2015. And so we're really, really honest. You can tell by the way I'm talking about it. It's something we're really very, very proud of. And then these longer timescales. This is really new turf. We're just getting started and looking at this and thinking about, can we tell you, next king tide season, for example, there's going to be in October, there's going to be, 20 flooding days instead of 10 flooding days, or what's the risk of there being 20 flooding days? So we're still getting going on that. But I'm not going to talk too much about that. And then decadal forecasts, climate change gets involved in that. And very, very low frequency variability in the ocean. Touch on that a little bit, but most of the talk, we're going to be talking about these two time scales. What's going to happen 3 to 4 weeks from now, and what's going to happen 3 months from now. Okay, so the reason I think, one of the big reasons anyways, an example of why I think I can tell you something about what's going to happen 3 to 4 weeks from today is this thing called the Madden Julian oscillation. And what you're looking at here in this picture, this is a blob of very heavy rainfall, and this is a blob of very, very little rainfall, or effectively none. These are deviations about normal, so it looks like it's negative, right? And this blob of heavy rainfall propagates across the Pacific Basin. And this blob of decreased rainfall propagates across the Pacific Basin. And as this rainfall blob is propagating across, it's disturbing weather globally, and that's moving across. And so eventually, when it gets all the way out here in the Pacific, it actually disturbs weather all the way in the Atlantic. And here's the example. This, when it's in its what's called its westerly phase, you can see there's lots of hurricane tracks, lots of hurricanes happening. But when it's in its easterly phase, which is right around in here in this plot, in its easterly phase, there's very few hurricanes. So if I can predict this blob, this Madden Julian oscillation blob, if I can predict it, I can say something about hurricanes 3 or 4 weeks in advance. So that would be pretty powerful. And I'll show you an example where we think we succeeded. Now, I said that I wanted to talk about not only subseasonal, but the seasonal forecast, a little bit longer time scale, what's going to happen a few months from today. But this specific example is really drilling down to that question of why do I think I can predict something beyond that 10-day weather time scale? And so this example I'm giving you is really a stark example. So it's really sort of getting the best possible result. All right. So here's my example. This is a picture of what the sea surface temperature, the ocean temperature at the surface looks like during an El Nino, during a big El Nino. So here's the big El Nino. This is deviation about normal. So it's what we call an anomaly. You've probably heard that before. And so during an El Nino, you have this big blob of warm water. And when you have this big blob of warm water, you get lots of rainfall in this black box. It rains very heavy in this black box. During a La Nina, you get a big blob of cold water, not quite as impressive as the El Nino, but what it does is you get almost no rainfall at all in that black box. Okay, so let's look at our tools, our models. These are computer models that are quite sophisticated. They solve very complex equations. They require enormous data set feeds from observations of the state of the climate system that are instantaneously taken all over the globe. So you can imagine the systems integration component of bringing all this together is an enormous enterprise with many, many moving parts. All right, so let's take a look. We do a forecast. So what I'm doing here, what I'm showing you a picture of, is I'm showing you a picture of the rainfall in that black box, okay? And I'm doing it over and over and over again. And I have to do it over and over again because I want to get the statistics of the weather in that black box, the statistics of the rainfall. I can't just do it really once and then I got it right. So I do it over and over again. And so these red dashed curves are me getting those statistics of the weather during that El Nino event. And the blue is during the La Nina event. And so there's two big things that happen here. In the early part, as you can see, the curves stay very close together. First 10 or 14 days, the curves stay very close together. That happens in both the blue and the red. That's that weather timescale. That's the fact that I can actually predict the weather, 10 days out. When you go out here, way out here, they're all over the place. They're bouncing around. So I couldn't tell you on June, the day 70, whether you should have an outdoor wedding. But I could tell you something about the statistics of your wedding in the middle of the ocean, but that's neither here nor there. And the other thing you see is the red curves are displaced, right? They're clearly separate visions of the world in the El Nino than in the La Nina. They're really well separated. In this example, I've chosen it carefully so I get that big signal. When you get away from here, then it's not so simple. It requires some careful statistics and analysis. But in this example, the red curves are very, very different. Now, there's a subtle feature here, a really most important one. And this is kind of the real target, the real thing we're looking for. The red curves bounce around much, much more than the blue curves, right? Big oscillations in the red curves, much more extremes. In the blue curves, very few extremes. And so it's these extreme events, the change in the statistics, not just the mean value that the red curves are separated from the blue curves, but that the red curves are bouncing around much more than the blue curves. It's that we want to be able to predict. And that's where the real challenges come. This is where the extreme weather comes from. This is where the hurricanes, forest fires, and all that stuff, the increased chances of that coming is being able to get the statistics of these bouncing curves right. Okay. So we did the MJO, that blob propagating across the ocean. That was the 3 to week 3, 4 hazards forecast, the MJO, I could do, more hurricanes, less hurricanes. The second example I just did was El Nino, which has a seasonal timescale, happens over sort of 6 to 9 months, and we think we can predict that. And then there's multi-decadal timescales, and so you can see a blob of warm water throughout much of the North Atlantic. This is called the Atlantic Multi-Decadal Oscillation. It has a very low frequency, and it affects weather and climate worldwide. And if we could predict that, we think we could predict changes in low frequency variability in tropical cyclone counts, for example. So what you see here in the black curve is tropical cyclone counts on a 5-year average timescale. And you can see it's pretty well correlated to when that blob of warm water is warm, or whether that North Atlantic water is cold, relatively cold. So again, if we can predict that Atlantic multi-decadal oscillation, we might be able to say something about the chances of tropical hurricanes. Over a 5-year period, there might be less versus another epoch where there might be more. So all these forecasts that we're talking about, they must be in terms of probabilities. And that means we need to run lots of realizations, like those examples I showed with the red and the blue curves. There were lots of realizations. But we've also learned, and this is really what's important, is that it's a diversity of models, because some models are good at this and other models aren't. And you really want to have just like a diversity of ideas whenever you have to make a big decision. So it's the diversity of models that make a really powerful tool in making a better risk forecast. And it's that systems integration of bringing all these modeling tools together. That's where the University of Miami really is leading the effort. So it's kind of like, the components of the airplane are built by a bunch of different people, but bringing all those components together and making sure they work, that's really important. That's the systems integration part that we do in terms of this problem. Okay. So let me start by looking at some of these seasonal forecasts, this a little bit longer time scale that's a little bit more mature. In the project here, you notice this is a screenshot from a NOAA website. This is a NOAA website. And the reason it's a NOAA website is this project, the North American Multi-Model Ensemble system, which I'm going to call it NMME really fast. And it doesn't mean it's my enemy. It sounds like I'm saying enemy, but it's actually something I'm really quite very proud of. This North American Multi-Model Ensemble, or NMME, is a project that we run here at the University of Miami. And we started back in 2009 working on this project. And it took us 6 years, a little over 6 years, to make that system, get that system approved as an operational product. And so now, it started actually in late 2015, this is an official forecast product of the National Weather Service, NOAA. And we continue to lead that effort. We continue to do the system integration. We continue to do the model improvement. We continue to work on that system and continue to do science. And I'm going to talk about some of those things more. And the winning result, this is a picture of the winning result that we were able to convince NOAA that they should take this new NMME system. Okay, so there's a lot going on here, and I'll try to explain it. It's the picture is a metric of how well we forecast rainfall, and it's called a rank probability skill score. And the way this metric works is if it's more positive, more red and yellow, then there's more economic value in our forecasts. And if it's blue, there's much less economic value. In fact, you're better off guessing if it's blue. Okay, so you're actually doing worse. And now this bottom plot, before the NMME project became operational, this was the NOAA forecast that they were making, NOAA forecast, and this is how good it was. And so you can see there's quite a bit of blue, a little bit of red out here, which is good, but too much blue, way too much blue. And what's really fortuitous for us NMME guys is we really improved the rainfall forecast in Florida and the Southeast U.S., but also out here in the Southwest. So we really did have a big boost in a lot more red, a lot more orange here. And equally important, we reduced the amount of blue. And so based on these results, and a number of others, of course, Noaa decided to make this their official seasonal forecast tool. Hurricanes. The NMME system is used today to make the hurricane forecast. And in fact, the forecast that we're going to start to run on Thursday, April 1st, we start to run them on Thursday, April 1st. Those forecasts will be used to build the hurricane forecast for this coming season. So the first outlook for the hurricane season will be issued on around April 15th. That hurricane forecast outlook will be based in part on these NMME forecasts. And you can see I just highlighted down here in the bottom that if you look at a bunch of different tools and models, it's always turns out that it's the NMME tool that tends to have the best skill scores. In this case, you want the smallest root mean squared error, and you want the biggest correlation coefficient. So we rank run in both of those for the NMME system. And this is just giving you an outlook what we forecasted last year, last hurricane season, and that there's an 85% chance that it was going to be above normal. And of course, that forecast came to be true. It was quite a bit above normal. So look, April 15th or so, the NOAA will issue its hurricane forecast for 2021, and that forecast will be largely based on this NMME product. I'm going to skip this slide and just start moving into the subseasonal timescales, because I can see I'm chewing up quite a bit of time here. So the subseasonal, our goal here is, again, that same systems integration. And in fact, Noaa came to us again and said, look, can you guys try to build a systems integration system that you built for seasonal? Can you do it for subseasonal? And we said yes. We've taken that on. It's harder. It's much harder. And you can see the skill at, making a week 3-4 forecast. You would have thought, because it's closer to in lead time, it's only 3 or 4 weeks in advance as opposed to seasons in advance, we should do better. Surprisingly, that's not true. And the reason that's not true is because our weeks 3 and 4 is a smaller time period to get those statistics right. Whereas when you talk about a season, you're saying, well, I want to get the statistics right over 90 days. So that's the big difference, is this temporal scale that we're trying to forecast the statistics for. So this subseasonal timescale is turning out to be a real big challenge. We've built the system, we're testing the system, and I'm going to show you some results. And we're still working with Noaa to make sure that they ultimately can approve, sanction, yes, boom, this is the way we're going to make our week 3-4 hazards forecast. But we're still working on that part. So if you remember, I started out with this picture not too far where I grew up. This is actually right along the coast. And this was on January 8th. This picture was taken, and this picture was on January 25th after the mudslides had careened through the area. And there was a number of people perished. It was really, really a big event. It happened, I think it happened around the 20th of the big slides happened around the 20th. This is a little bit earlier forecast. So maybe the slides happened a little bit earlier, but this is our forecast that we make here at the Rosenstiel School for Montecito. It's a 3-week lead, valid in the week ending on January 12th in 2018. And you can see there's this really large blob of rainfall coming into the west coast of California in that forecast system. This is called an atmospheric river. And this, our forecast system picked that up 3 weeks in advance before. Now, someday at the time, it wasn't an operational system. No one was asking, should we trust this forecast? Someday, we hope that they do trust these forecasts and people start to make decisions in order to protect life and property based on these forecasts. This is another example. This is hurricanes. This is Isaias fairly recently, January 20, from August 2020, early August. And so here's a picture of the forecasted track of Isaias, and here's the actual rainfall from Isaias, and these two plots are our week 3 and 4 forecast from this UM-led subseasonal prediction experiment for the rainfall valid ending the 2-week period ending August 7th, and then you can see the 2-week period a little bit earlier. So you're sort of capturing the track of the storm, and then later all the rainfall throughout the Mid-Atlantic and North Atlantic coasts of U.S. Really quite remarkable. We have a number of examples. Okay, so everything's terrific, right? You know, a typical modeler like myself using computer models, I always brag about how good the models are, but then 10 seconds later, I start bashing the models. The models are terrible. We need to make much more investment to try to make the models better. But here's an example of a sort of a glaring issue with these models that really, at first it doesn't, you're sort of thinking, what's the big deal here? This is that same skill metric that's connected to economic value. It's called, again, rank probability skill score. And so it's how well do I predict the distribution of sea surface temperatures across the globe, the entire globe. And as I mentioned, everywhere that it's red, that's good. And the tropical Pacific here, where it's all red, that's really important, because that is, you remember the blob that's propagating across, that's affected by those temperatures, and El Nino, and getting all those things right. It's good to be able to forecast the sea surface temperatures right. That's going to be really helpful. What's interesting about this plot is where it's blue, and where it's blue, I would be better off guessing. Just random guesses would be better. And so what this is saying is that my model is worse than guessing where it's deep blue. It's worse. That's to me, that's important information. That tells me, boy, there's something fundamentally wrong with what my models are doing. I should be able to fix that. That should be a big challenge for me. I need to fix that. And where this is occurring, where I'm getting all that blue are really interesting places throughout the globe. In the North Atlantic here, this is in the Gulf Stream. This is right in the Gulf Stream. In the Pacific, this is in the western boundary current of the Pacific. It's sort of analogous to the Gulf Stream. It's called the Curacao Extension, another western boundary current. Out here is a western boundary current off the coast of Brazil, another important current system. Down throughout here, these are a huge current system in the Southern Ocean. Again, a current system, these are all current systems that are really fast currents for the ocean, and lots of ocean eddy activity. So we're hypothesizing here at the University of Miami that the problem is we're doing the eddies in the ocean wrong. We need to do a much better job of how we represent how the eddies in the ocean work. And so that's what we're focused on in terms of, can we do better? Okay, so sorry about the slide, the drawing there. I don't know why I didn't because it's just sitting on top. Sorry, it's sitting on top. I apologize for that. So this is a picture of our development efforts in trying to do a better job of representing those processes and current systems in the ocean. So this first panel that says traditional model, this is the model that goes into that NMME system and that subseasonal or sub-X prediction system. And most disturbingly, this is what the models look like for our climate change assessments, or how we predict that the climate's going to change in the next 100 years. So, and I'm going to show you something a little more in a second, but what you can see is these currents don't look particularly realistic, and they're sort of anemic and weak, not very strong. This is the tool we're developing on this right-hand panel. This is the tool we're developing here at UM. And what I'm going to show you in a few minutes is I'm going to show you how this system evolves over time. But you can see there are much tighter, interesting features, lots of eddy activity. You get these loop current rings. I want you to watch for these loop current rings. And in fact, this high resolution system, hurricanes can get trapped because it's a warm core. It's really warm in the middle here. And hurricanes can get trapped in that core of that loop current and can really intensify. None of those features are present in these more traditional models. So what we're fundamentally arguing is that what's happening in the ocean, what's happening in the nearby ocean is affecting the weather statistics over North America. Okay. All right. So this first video that I'm going to be showing, Justin's going to queue up for you in a second here. This is the boring movie. Okay. This is and I apologize. It takes about 20 seconds to run or so, and it doesn't look like all that much is happening. It's a real boring video, and what it's showing is the evolution over a 10-year period of what the currents look like in that standard climate model simulation. The standard climate model simulation. So it's the boring movie. Okay, nothing much is happening, only lasted around 20 seconds. But all those features I talked about, the Gulf Stream, the eddies, the loop current, that's not there. The next movie, the next one that I'm going to show, and Justin's going to cue that one up, the next one, is on slide 25, Justin. And the second one, oops, he's showing slide 24, I believe. So that's the boring one. Let's let that boring one run. It's 20 seconds of a boring video. I apologize for that. The next one that we're going to show in just a second, Justin will cue that up, is the Academy Award winner. Okay, that's our new model. Here it is, and you can see there's those loop current eddies that shed off. There's the wiggling of the Gulf Stream. That's all critically important in terms of getting the weather and climate over the U.S. better. Even on these week 3, 4 timescales, even on these relatively short timescales. And I'm going to show you some examples of that in just a second. All right. So here I want to show you an example. This is a really nice example. This is some work that I've been doing with one of my graduate students, and it's turning out to really be very influential work. It's caught a lot of attention already. And I just want to emphasize the pictures in this green box. Okay, and this is the interaction between the seasonal time scale, the El Nino stuff, and the subseasonal time scale, the MJO stuff. And so what this picture in the green box is what happened in nature. So this is that MJO coming through, and that's what it produced in terms of rainfall over the U.S. During the 1997-98 warm period where there was a warm El Nino going on. This is the amount of rainfall that we can blame just on El Nino. And so just looking at these two pictures, this fast moving thing can completely overwhelm the El Nino thing that sits there for 90 days or more. Okay. And so for a short period of time, 2 weeks or so, you get this big burst of rainfall that sits on top of the El Nino. And the question is, can we forecast that? Can we get that right? And this is the combination of both of them. So let's see how we did predicting that 97-98 period where this MJO whipped through and there was an El Nino going on. Let's see how well we do. So the top panel here is those 3 pictures that we just did. This is that MJO phase from observational estimates. This is what's going on with the El Nino, and this is what's the combination of both. And the bottom panel here, the first one, this is our standard NMME forecast that I label low resolution. Low is not fair, it's sort of medium, it's what's the standard. And you can see it got the rainfall over, got lots of rainfall over the ocean, gets that El Nino signal over land, but not so much this big amplification of the event. This picture now, this is our new model. This is our model that's getting the currents right. That gets that, that corresponds to that Academy Award winning video. And you can see big rainfall anomaly, and it's over the land. It's doing it in the right place. And you can see the dryness near where the ocean currents are. That's the critical part. This guy's not getting that, whereas this guy is. It's getting that shift of the rainfall inland over land that's associated with this big MJO event. And this hard to look at picture is the physical mechanisms. We really understand that. What this picture is you want to think about this is how the winds circulate. Think about this as how the winds circulate. So in this plot, the winds are going counterclockwise here, and they're going clockwise there. They circulate around like that, and they circulate around like that. That's that MJO signal. And so you can see that MJO signal wants to bring all this moisture up from the Gulf of Mexico to give that rainfall over land. Right? So that's the MJO signal. The signal associated with just the ENSO part, not quite so good, not quite so strong. And then, of course, the combination of the two is really strong, bringing that Gulf moisture inland. This is that low resolution forecast, kind of looks more like this, whereas the high resolution model is doing a whole lot better job of capturing that circulation and rainfall that comes in over land. Really, really a nice example of how important it is to get the stuff that's going on over the ocean, getting the stuff that's going on over the ocean right. And we think we can only do that with that system that is actually resolving the currents correctly. This is just another example, and I apologize, it's a horribly busy slide, so I want to apologize that it's at the outset for that. I just want to focus in on this panel first. And what this is showing you is that the importance of the ocean currents all the way out near Japan and that Curacao Extension, all the way out here in Japan, are important for California rainfall. And what this plot is showing you is when those currents are really strong versus when those currents are really weak out there, how it affects rainfall. So when the currents are strong, you get big rainfall anomalies, big positive rainfall anomalies. And when those currents are weak, you don't get much rainfall at all. That high resolution model is able to capture that, or at least some elements of that. The lower resolution model, not so much. And what these curves over here show, is that when you look at the rainfall distribution, this is called a cumulative distribution. I apologize for the technical aspects of it, but you can see the blue curve and the orange curve are well separated here. And that's because it's capturing those different phases of what's going on in the ocean off the coast of Japan. Whereas the low resolution model can't do that, can't capture those differences, whereas the high resolution model does. So that those current systems turn out to be really, really important. All right, so then I started with this notion that I'm doing really bad where the currents are blue, where this skill score is blue, this ranked probability skill score. I noted that these are all happening in these western boundary current regions. And I looked at the skill score of that traditional model, and it had weak economic value in those regions. We go to this much higher resolution model, this model that captures those current systems much better. It's not perfect. The skill's not as good as it is in the tropical Pacific. That's a big target for us. We still have work to do. But boy, we've knocked down a lot of that blue. We've knocked it down in some regions. We've even introduced some red. So in the Gulf, in the Gulf Stream, we're actually doing quite a bit better. And if you look in the Gulf of Mexico, remember I made a big deal over those loop current eddies in the Gulf of Mexico, right? It's blue in this low resolution model, but in the high resolution model, it starts to pop red. So we're actually doing something a lot better in the Gulf of Mexico. Also, so just a couple more slides. This picture, it's a teaser because we're starting to work at those longer time scales, multiple years. Can I go a full year from today, or can I go 5 years from today? So these multi-year to decadal kinds of time scales. And this high resolution model that's capturing how the Gulf Stream works is going to be critically important to success there. And the example I raised was this notion of predicting coastal flood risk, right? So are we gonna have more flooding events this coming king tide season next October, or are we gonna have less? So long lead, or maybe for the next 5 Octobers, long lead king tide flooding events. What this picture is showing you is how flooding at Virginia Key, this is at Virginia Key, this is where the Rosenstiel campus sits, how flooding at Virginia Key is related to the strength of those currents that we talked about, the Gulf Stream. If I made this plot in that low resolution model, you wouldn't see any colors at all. It would be completely blank. But in this high resolution model, what you see very clearly is when the Gulf Stream weakens, these negative values mean that the Gulf Stream is weakened. When the Gulf Stream is weaker, the current is not as strong, the risk of coastal flooding goes up. So weaker currents mean that the sea level at Virginia Key and many other stations, the sea level rises. And so the risk of coastal flooding rises. And this model is able to capture that interplay between the strength of the current and the flood risk at the coast. And so the question is, if we can demonstrate that this model can predict changes over multiple year timescales, changes in the strength of that current, will it be able to predict the flood risk for the Rosenstiel campus? So that's one of the areas that we're pursuing as we go forward. And the last slide I want to show is, before I take questions, is I'm showing you a real forecast. These were forecasts. This one in particular was issued March 26th. So these sub-X forecasts we do once a week, but this forecast was issued March 26th, so just a few days ago. It's valid for the 2 week period from April 9th to April 23rd. And what it's showing is, boy, in a big chunk in the eastern half of the U.S., we're expecting relatively dry conditions for this compared to before. And notice it's published as a probability, right? And this is one of the things that I wanted to emphasize. We have all of these different tools, model tools that we developed, modeling tools that NASA developed, modeling tools that the Canadians developed. We have all these different modeling tools. Our systems integration is to combine all these tools to produce a single probabilistic forecast that people can take action on. So we're expecting dry conditions during this 2 week period in much of the eastern half of the U.S. and in even a significant chunk of the western third or western sixth of the U.S. As we go out to longer lead time scales, right? So this was a forecast that was issued for the beginning of March. So we don't, on the NMME forecast, we don't start issuing the forecast until the beginning of the month. So we're going to, in fact, when this call is over, I have a conference call with the team, and it's, where are we? How are the forecasts? Are we going to be on time? Because we have to deliver on time, in real time, all the time. There's no, we can't not succeed. There's no, it's not acceptable. It just can't happen. So we have to be very careful to make sure we're ready. We have fault tolerances, and we're able to deliver those forecasts on time. This is for the coming April, May, June season, and it's predicting, quite dry conditions throughout much of the U.S. So test me, take a picture of it, see if we're right, hold our feet to the fire. Did this forecast verify? So thank you very much. I'm quite happy to take any questions or any comments. So let me bring up the chat. We have several questions. Let's see. The first one I can see is, do I have any international partners or international joint projects? Yes, very much so. So the Canadians are key team members in both of these, the NMME project, they're key partners, and in the Sub-X project, also the Subseasonal project. The Canadian Weather Service, their equivalent of our National Weather Service, are key partners in that project. I have international partnerships with the members of the INPE, which I guess is the equivalent to the Brazilian NASA. And they're partners, and we're trying to exchange forecasts so that they can do a better job of predicting what's going on in Brazil and off the coast there. And we can learn a great deal from them in terms of their local knowledge of how the climate system works. So we do have lots of international partners. And some of the NMME team members also have separate international partners. And there's a big effort in using those NMME forecasts to make climate forecasts in developing nations, particularly in Africa. That's really, really important because so many of those nations rely on agriculture. And so if it's a poor, if they need to plan, if they're not going to have enough rainfall, or plant drought-resistant seed, or figure out different irrigation strategies. So there's lots of issues there. How can communities better prepare and respond to the impacts of climate change? Really important question. And I actually, I do give lots of climate change talks. One of the things that I think is, as we work to adapt to these shorter time scales, so extreme events on seasonal time scales and subseasonal time scales, and start working to the multi-year and the decadal time scales, that's going to teach us how to adapt to long-term climate change. We're going to get better at it. It's like making automobiles. Cars just keep getting better and better. Airplanes keep getting better and better. As we practice on dealing with real events, we're going to get better. So we need to learn how to use those forecasts to help us make decisions to mitigate and adapt. And we need to do the same thing on the very long time scales of climate change. So the two are really intimately connected. What can we do as citizens to help end the climate crisis? I think it's a really important question. My personal belief is everybody has to do everything that they can do. We really do need to take this holistic or a shotgun approach to dealing with the challenges of climate change that we have before us. And so, yes, you should, drive less, figure out ways of commuting less, use a vehicle, take public transportation, use vehicles that are electric or hybrid. But that's not enough. Every person has to do everything they can do. We want to make sure we don't think, well, I did this one thing, I recycle, therefore I'm done. No, we have to do everything. We have to take a very holistic approach and encourage our governments and political leaders to start really being very serious about making sure our communities adapt to the challenges that are climate change, but then also we start to mitigate the causes of climate change. We start reducing our carbon footprint as best as possible. And I think I covered, I apologize, I'm working the two screens at once. And so the above three questions are to answer, then go to talk. Okay, so sorry, I was reading out loud. Just to close here, folks, I really want to thank you again for attending this lecture. I hope you found it informative and valuable. And there's a networking session that starts at 2:30 today. I'll be attending that. And if you have any questions, you can ask me about weather and climate, or you can ask me about anything, graduate school, if you're interested in graduate school, or how did I get started? I'm really originally a mathematician, so this was a leap for me to get involved in weather and climate. So anything about any questions are on the table. And coming up next, I want to welcome our host. Xavier will introduce a video of Lakeside Village, followed by the keynote session, which I believe is starting promptly at noon. So once again, thank you very much for your attention, and I hope it was informative, and I look forward to meeting you all in person as best as possible in this virtual world at the 2:30 networking session. So thank you very much.